Hey everyone, today I want to talk about background jobs in Node.js with BullMQ. My name is Douglas. I'm developing for the web with TypeScript, React, and Rails for about 5 years now, and I'm currently working at CodeMiner 42. Today you see here that BullMQ allows you to make better use of the host resources, and that's because some tasks are better done behind the curtains. We'll show you what's the most obvious strategy to run BullMQ and why that's not necessarily the best. And also I'll show you some wiser ways to run a BullMQ worker, so you really benefit from it. To follow this talk, I want you to have some experience with JavaScript, and that is having already set up a local web server. Pretty simple thing. I want you to have some basic understanding of how to handle promises as well, such as whenever we call a database or an API, it's usually an asynchronous call, so we will need to wait for it to respond. With that, you should already know that there is an event loop behind the scenes that allows Node to push tasks to a queue and executes a task that is ready to be executed one at a time. To review it, I recommend you watching the Monitoring Event Loop Lag in Node.js, in a Node.js application by Paulo Souza from a couple of weeks ago. And let's start talking about concurrency. We know that JavaScript is single-threaded, and so are its runtimes. With that, Node.js will handle one thing at a time. And things that take too much processing time will delay other things, especially if we're executing them. The work that is done is in the same process thread. Input and output operations are done in separate threads handled by the famous libuv. And Node.js will watch a micro task queue to orchestrate which task is ready to be run and then which runs when. This talk is about a web application such as any REST API or anything served over HTTPS. And with that, some features should not affect the response time, such as like we're going to generate an email to confirm users' actions, like recovering passwords or registering a user. That does not need to affect the response time. Or if we want to periodically pull data from a weather API, or if we calculate something after user plays some action, such as a monetary transaction that the user inputs, and we want to sum up their balance. It probably does not make sense to do that and let the user wait for the response. We can do that in the background. So let's start by building the simple server with Fastify. There's nothing much important or hard here. I basically set a root route that will log requests received, and the server will listen to the port 5000. The important things here are the logs. I will log that I received a request. I will log that the server is running. By running this server, I will have the logs as below. As soon as a request hits, it will log request received. Running that, I can inspect my activity monitor that I will see that I have only one Node.js process with 12 threads. So let's push some tasks to the background. First, we'll need to understand what the background flow will be like. We have the queue, we have the worker, and we have someone such as the server that will push jobs to the queue with some properties or job data. And eventually the worker will watch that queue and pull a job from this queue to execute it. That's the basic structure. We have the worker, we have the queue, we have someone such as the server pushing jobs to that queue. Right, so for us to build our queue, please take a look at this. The handler is pretty much the same for the Fastify, for the route, that will log request received, that then it will log that it's in queuing a job, and then we will need to push some jobs to that queue. First, we will build the queue, importing the class from the BullMQ library, and call the method add to that queue. The first parameter will be the job name, and the second parameter will be the job data. We don't need data for this example, so an empty object will suffice. Also, notice that I've wrapped the server construction in a build server function to ease the syntax that we'll see further. I have to build the worker then. I will import the class worker from the BullMQ. I will wrap in a run workers function. And as soon as I create this class worker with the proper parameters, it will start watching the queue and start processing jobs, unless I tell otherwise. But in this case, we'll have the default configuration to pull jobs from the queue as soon as the worker exists as an instance. The important parameter here is the second parameter, that is the handler function. The handler function will basically receive a job and will log that it's processing the job in the job ID. That's the work that we need done. Right, so if we have the build server and the run workers function on the same entry point and we run both of them, we should have a server listening to a port and workers watching a queue. Cool. If we inspect the activity monitor again, we will have only one process with 12 threads. And if we hit a request to that route that we made, we will notice that it receives a request and queues a job and then processes the job one thing at a time in a specific order. Cool. That is because JavaScript is single threaded. And if the worker takes long to resolve, other requests will need to wait, or the other way around. If the server is too busy, the worker will need to wait. It can only process one thing at a time. That is what we call blocking the event loop. So let's leverage on parallelism. We have this structure here right now. We have the web server running upon a NodeJS instance, and we have BullMQ running on the same NodeJS instance. Notice on the right that BullMQ also relies on Redis. It's where the queue will exist. It's an external service, but we won't get deep into it. What I want to show is that we might want some structure like this. We want to have a web server with its own Node.js instance, and we want to have BullMQ with its own Node.js instance, so they don't bump into each other to do work. Right. To achieve that, we will need to have two entry points. The first I will make is the workers.ts that will basically implement the same function that we saw before, which is the run workers function. Doesn't do much. I just added this new log line to say that the workers are starting. Cool. That's one entry point. And the other entry point is the servers.ts. I didn't touch anything on it. I just separated the worker script to be run in a separate command. Right, so npm start will start our server. The server will start listening. And if we start the workers will be watching the queue. Cool. We now have two processes, each with 12 threads. If I hit the request on the process one that is listening in the port 3000, I will see the logs that I received the request and I am in queuing a job. And the process two will start the workers and eventually will start processing the jobs. Great, we have some parallelism now. Those are the two simple approaches that we can make. The first uses the same process. It shares the same JavaScript thread, shares other utility and infrastructure threads, and takes no advantage from parallel processing. It will be concurrent with other code running on the same process as well. But if we have two processes, we will have one entire node process for each, and it will share pretty much nothing. But the operational system will handle how parallel it will be. That is because the orchestration will be part of the OS routine. It will allocate which process will run when. Some deployment platforms might not allow multiple processes. You might notice that with cheap instances of deployment, you might be able to run just a few, like 1 or 2, even 4 processes at a time. So that's a blocker sometimes. Right, we have work being done. So is there a way to make workers work more? Of course there is. So first, we need to identify the work nature. Is it the work CPU intensive, such as calculations or parsing? If so, we will need more JavaScript. And if we need more JavaScript to run in parallel, we will need to have more processor cores, as we might have noticed already. Or is it the work I/O intensive? Are we calling many external services, APIs, databases, or stuff like that? If so, Node already shines handling those with the event loop. So there's no need to have more cores. It's just a matter of concurrency will solve our issue. So local concurrency is the first parameter that we can tweak in the BullMQ configuration to achieve more work in less time or in the same amount of time. I've set the third parameter is the worker options. There's this concurrency parameter that I set to 42 for no reason that will allow the worker to pull up to 42 jobs from the queue at the same time. It will shine if we have an asynchronous call, as I faked here, by resolving this promise that will take 1 second to complete the job. I will postpone the job completion to 1 second. And after that, I will log that the job is completed. The job completion will be blocked by this promise that will take a while to resolve. Right, let's enhance the challenge for the worker then to enqueue 100 jobs, such as if we were going to send 100 emails, or we are emailing to 100 people. That's a somewhat common use case in web applications. Right, starting the server and the workers. I have the server listening on the left and the workers watching on the right. I have 2 processes, each with 12 threads. And notice that now I have many jobs being processed on the left. Then 42 jobs are completed just on its side. But I wanted to take a look at this red square, that when the job 50 was completed, it started processing the job number 85. And then it started processing the 86 and 87. And just then it completed the job 51. That's because the delay for those were not complete at that time. So it had some free time. So it watched the queue, saw that there were more jobs to be taken, and started working on them. So the completion is not linear if we are going to do concurrent work. And that's not a problem at all. It's just the worker just doesn't have if it has free time, it will use it to do more work. That's actually good for our application, depending on our use case. Right. With that, I have 2 processes, one for the BullMQ and one for the server, each with an average of 55 megabytes, which is pretty reasonable. There's not much work or code running in each process, so that's a pretty low amount of memory, each with 12 threads. Right, so the event loop is what allows concurrency, because if JavaScript can make free time to push tasks to be worked on later. That's the task queue. BullMQ itself has an inner loop that will pull more jobs from the queue up to the amount that we set on the concurrency factor, that we can set higher for IO intensive work. And if we have CPU intensive work, we won't take any advantages from it being high. So that's okay to leave it as a low value then. So another strategy that we can do to make workers work more is to have sandboxed workers. What's that? Sandboxed workers can use worker threads or child processes. Each thread will have a V8 instance in it. That means it will run its own JavaScript. And it takes a certain amount of memory, but not as much as if we would spawn a process that will have a full node process in it with all its 12 threads. By the way, those 12 threads, only one of them will be JavaScript running, and around 4 of them by default will be IO threads and such. Having a full process, a node process, will provide you all the infrastructure and all the threads that a regular node process spawns. To have a sandbox worker, we must extract the job handler to a file of its own, a module of its own. Then we need to export the handler function, similar to this. I've grabbed the handler function that we had inside declared in line with the worker, but now I have this worker processor.ts file. And it does pretty much the same thing. Logs that it's processing the job, waits for 1 second, and then completes the job. Marks the job as completed. And we can still import it as a function, a normal function, and pass it to the constructor. The constructor, the worker will work the same, exactly the same. But the trick lies here. If we, instead of passing the function import, we pass the path import, pass that to the, I've extracted the worker creation to this create worker function, where I pass the processor path, not the function itself, not the function import, but the path to the second parameter of the worker. Calling this create worker should create the worker and have a worker running and watching the queue. That's only one worker with using this use worker threads option equals true, and the concurrency factor I kept as 42. Right, if I run the server, I'll have the server listening, and if I run the sandbox workers, I'll have the workers watching. Looking at the activity monitor, I still have 2 processes as expected, but as soon as a request hits, I have 54 threads and 1.3 gigabytes of memory taken. That's interesting because it will have the 12 base threads plus 42 threads that it will use to do work, each thread having its own JavaScript running in it. Notice that after some time, garbage collector collects garbage, and we reduce the amount of memory to 168 megabytes on a idle state. It's quite a lot still, but that's the cost to have more threads spawned. To have the other approach is that we can spawn processes. We can have child processes. We just comment out this use worker threads. We keep the concurrency factor to 42. And again, running those, I will have the same 12 threads, 2 processes with around 55 megabytes. But as soon as a request arrives and queuing 100 jobs, it will spawn a lot of processes. You can already see that it will take a lot of memory. And yeah, I have the concurrency factor of 42. It will spawn 42 new processes. Looking closer on them, each process will have around 55 megabytes and 12 threads each. So that's quite a lot. If we do some calculations, 55 megabytes times 42 processes, we will be taking 2.3 gigabytes in contrast with the idle state of 850 megabytes using threads. But that's the cost we have to have a full-fledged NodeJS process with all the infrastructure available for the work to be done. So those are the alternative approaches that we have. We have the worker strategies that we can do it concurrently with the local concurrency factor. It's good for I/O. It will use the same process and the same thread, but we can do it sandboxed. It's how BullMQ calls the kind of worker. It's sandboxed workers. Those can be sandboxed worker threads, or that will consume less resources than the whole process, of course. Shares resources, such as the I/O threads. Then you can think that if you're doing some work that is I/O intensive, you probably gonna have some bottleneck. So that's up to fine tuning. Or we can have the child process approach, other than the worker thread. It will run a full Node.js process with all the threads available, will offer process isolation, but will consume more resources. And again, it might be impossible in some deployments. Yet another alternative that you can do is to use more computers. If we don't have terminals available to run more workers, more instances of workers, we can hire more computers to run more workers in parallel. It will depend on the need that we have. So the conclusions that I want you to take away from this talk is that you can run your worker on the server process, but you maybe should not. To figure that out, you will need to identify the work nature before you decide your worker strategy. So the code shown in this talk is available in this GitHub link. It will probably be on the description later on. And I think that's it for today. Thank you.